Good morning, all. Good morning. If my voice is audible to you. Hello. Yes, anyone please reply. My voice is audible to you.
Yes, sir.
Yes, sir.
Okay, good.
Yes, sir.
Let's
Yes,
start.
sir.
Right. Okay. Carry on. Yes. I want to repeat some yesterday's lesson because we are using the whiteboard yesterday. It is not properly, I think, it is not properly conveyed. Again, I wrote this whatever the yesterday's notes. Yeah, this we had discussed yesterday is about the heterocyclic compounds. We up to we came in systematic nomenclature. This is a systematic nomenclature for the monocyclic compounds introduced by the Hans and by Widman. It is improved by the IUPAC later. Then any heterocyclic compound that should have the name. Therefore, it follows the nomenclature systematic nomenclature. For giving the nomenclature, it should follow these three words in its name. That is, one is the prefix, and another one is the root word or stem word, and another one is the suffix. Next, always the prefix indicates the heteroatom which is present in the heterocyclic compound. That heteroatom, suppose if it is O oxygen, then that heteroatom is the oxygen. Then we need to include the oxa. Nitrogen, we need to include the aza. If it is a sulfur, then we need to include the thia. If it is a selenium, sila. Next, tellurium, tellura. Phosphorus, phosphor. Arsenic, arsa. Silica, silicon, sila. Germanium, German, germa, boron, bora. Like heteroatoms, we need to indicate by the prefix word, that is that word with respect to the whatever the heteroatom present. Coming to the stem word, root word, size of the ring, and it indicates. This is also we are already study class. Now we are making this table. I have given for everything one example here. Suppose it is a three-membered ring. That is the unsaturated with nitrogen compound that is indicated with irine. That is one of the example. Azirine is a di-RINE, azirine. If it is the iridine, that is the azitidine, is the fully saturated nitrogen containing compound. Right. Next, irene, if it is the compound with oxygen without nitrogen, therefore it is indicated with the irene. Oxirane, if it is the oxygen heterocyclic, oxirane. Then next one is the saturated one, fully saturated oxygen heterocyclic compound. Therefore, it is comes under without nitrogen containing heterocyclic compound. Therefore, it's named as irene. That is the oxirane. Similarly, for every case, I have given the one example here: 8 azete, etidine, azitidine, ete, oxete, oxetane, ethane, oxetane. These are the examples. Next, 5-member ring, ol, azole, it is an unsaturated one. If it is a saturated one, olidine, azolidine, that is tetrahydropyrrole. Next, it is ol, only ol, that is oxole, oleine, oxolane, if it is a saturated one. Similarly, what is a 6-member ring? Azine, there is the INE, 6-member ring with unsaturation, nitrogen containing heterocyclic compound. Azine, if it is the saturated one, name, azanine, azanine, if it is the piperidine. Next, in, if it is the compound with unsaturation without nitrogen, that is the oxine, if it is the oxygen heterocyclic. Like, if it is the oxygen heterocyclic without nitrogen and fully saturated, that is called in the end with the A, that is oxane. Next, 7-member ring, epene with the nitrogen and unsaturated one. Epene is the saturated one. Azepine, if it is 7-member ring. If it is the sulfur containing compound, thia plus epene, thiapine. and epene with oxygen, oxapine, 7-member ring, eight-member ring, oxycine, osine, that is azosine, osine, azosine, osine, oxosine, okaine, oxocaine, right? This is the 8-member ring. Similarly, we can take the 9-member ring, azonine, azonine, oxonine, oxonine, like 10-member ring, isine, azisine, right? Icaine, azicaine, isine, oxycine, icaine, oxycaine, like that. We have given several compounds here, examples. Next, it is the acetylene. There is a 4H oxolidine. It is a fully saturated one. We can also include that 2, 3, 4, 5 tetrahydrocarbazole or tetrahydroazolidine, right? Next, to the state of hydrogens of saturation are indicated by this suffix or prefix, like that. If you like 1H, if a hydrogen at the first place, hydrogen is 1 hydro. If the second place, 2 hydrogens are there, 1 to dihydro or 1 comma 2 H dihydro compound, like that. We can give the nomenclature. I will provide the same notes for your reading purpose. Next, numbering of the heterocyclic ring becomes essential when we are indicating the substituents present on the ring. Okay, right here we have the 3 different compounds are there. The numbering process always starts from here. 1, 2, 3. That is the 3-methyl pyrrole or 3-methyl azole. Right. Similarly, 1, 2, 3, 4, 5. 2, 3 dimethyl azole. Similarly, okay, we can give which here the 2 kinds of numberings are there. 1, 2, 3, 4, 5. Right. 1, 2, 3, 4, 5. Both are correct, but the positions are not same. It is a 2, 4. It is also, no, it is a 3, actually 3, 5, but it is wrong, because here this methyl gets the lesser number for assigning the substitution. In general, IUPAC names, IUPAC nomenclature will follow here, right? Next, heteroatoms is assigned first number, or the and the substituents are for achieving the lesser number, you need to continue the numbering. Like if here the heteroatom is there, first you give the first number to the heteroatom, then continue the numbering. Here, whenever you are giving the number, we need to follow this priority. Okay, here. Whenever you are giving the number, suppose the more than one heteroatom is present, you need to give the numbering like this. First, oxygen gets the highest priority, then the sulfur, then the nitrogen, then the phosphorus, and the silicon. Right? What it indicates here? Look in here. This is the 6th group one. This is the also 6th group one. This is the 5th group one. Right? This is the 4th group. Now, in the group also, less atomic number is getting the highest priority. Whenever we are moving from top to down, its priority is decreasing. Oxygen and sulfur. Its atomic number is lesser than the sulfur. Therefore, oxygen gets the highest priority than the sulfur. Here, nitrogen and phosphor. Nitrogen and phosphorus both are having the same group, but even the nitrogen got the highest priority than the phosphor. Right? Silicon is the 4th group. Look at here. This is the 6th group element. This 2. This is the 5th group. This is the 4th group. Based on this criteria, we need to take the priorities. Based on the priority, we need to assign the names whenever the compound is having more than one heteroatom is present in it. Suppose here in this compound, my cursor is appearing to you. My cursor movement is, are you observing?
Yes, yes.
Right. I'm counting here, the oxygen and nitrogen is there. According to this priority, oxygen gets the highest priority, and 2, 3, 4, 6, 5-member ring. Then the indication is 1, 2, oxazole. This is the name, oxazole. Whenever you are giving the name, whatever the priority of the heteroatom gets first, most priority, then we need to include the first name as the suffix, then as the prefix, then the remaining heteroatom indicates the original heterocyclic. Look at here. This is the azole. Azole, which is having an oxo heteroatom. Similar. Look at here. Here only one heteroatom is there. Just simply 3-ethyl, 5-methyl azole. Right? When two heteroatoms, one is the sulfur, one is the nitrogen. Then 1,3 thiazole is correct. Number is starting with one from sulfur, 2, 3, 4, 5. Then 1,3 thiazole. You need to follow this order. Right. We have other examples. Suppose the same kind of heteroatoms are present more than one. Here the two nitrogen atoms are there. Therefore, we can use, suppose two nitrogen atoms are there, we can use the di. If the three nitrogens, we are using tri like that. Four nitrogens, we are using tetra. 5 nitrogens are there, we can use penta like that. That prefixes can be used before the original name. Right here, the two nitrogens are there whenever we are giving the number 1, 2, 3, 4, 5. That is called 1,2 diazole. Diazole. Right? This prefix we need to indicate. Here also, these are all these two are the isomers. 1, 2, 3, 4, 5. 1,3 diazole. This one is. If it is a three-membered ring, diazine, and this is a diazirine, it is the six-membered ring, diazine. Right? These are the simple nomenclature. Then we come into the nomenclature for fused rings. What are fused rings? We get here. Pyridine is a monocyclic system, and benzene. If these two both can combine together, that will lead to the formation of a quinoline. Right. Then it results if this benzene and pyridine both will be combined together through the sigma bond or a carbon-carbon double bond. Then this is known as fused heterocyclic compound. Fused heterocyclic compound. Now, this compound nomenclature is also important because when you move forward, we can see so many of fused heterocyclic compounds. Therefore, if you are not aware of the fused heterocyclic names, we would not understand the concepts, but whatever the related to those compounds. Okay, any compound is existing with two or more than two rings are known as the fused heterocyclic compounds. This is the definition of the fused ring system. Next, when you take this here, I'm taking several examples. Single heteroatom is present, then the name is given as follows. This is the heteroatom. Suppose this is the furan, furan, okay, or oxo. Then it is fused with benzene. Therefore, it is called benzofuran. Right. Whenever we are going to give the perfect name, IUPAC name, we need to start the numbering. In this case, start the numbering with the heteroatoms like here 1 on the oxygen, 2, 3, 4. This fused carbon is called as a 4A, 5, 6, 7, and 7A is the number. The number is denoted as 4A and 7A. So that is 4A and 7A. Or you can also give the number as sometimes it may be indicated as 5A. 5A, right? How it is 5A? Why it is 5A? Look at here. 1, 2, 3, 4, 5. You need to continue this heterocyclic up to this. Just forget about the fused ring for instance. Then you will continue the numbering. It will become say 4A, it will become say 5A. Then it is fused with benzene. Then the prefix is mentioned with benzo, whatever the carbocyclic is fused to heterocyclic, that is indicated with the prefix benzo. Then it is the furan, benzofuran. Then where it is fused? Where it is fused? Here we have this is the furan. We have the bonds A, B, C, D. Or this is the A, B, C. Or continue from here, A and B. Whenever we are labeling with these alphabets, we are finding three kinds of linkages in the bonds in the heterocyclic compounds. Now, whenever you are naming the again in this benzofuran, I am labeling this bond with A, this bond with B. Now the fused bond is B bond. The fused sigma bond is the sigma 1 5 bond is the B bond. Now the position is the B. Now that is clearly indicated benzo 4, 5. This is the bond B 4, 5. This is the fused bond. And that is the specific labeling is the B 4, 5 B furan. This is the perfect IUPAC name. Similar, you can this is having the quinoline is the common name. Whenever the trivial or common names are there, we can use very freely. IUPAC is also allowed us to using it. But whenever we are give the nomenclature, the single quinoline not appear in many cases. It will be substituted with the different kinds of rings, different kinds of substitutions. In such case, we need to give the perfect position of the substitution. In such case, we need to give the IUPAC name. Here, the carbocyclic is the benzene that is indicated with this prefix as benzo, and this is the pyridine ring. Then you give the numbering 1, 2, 3, 4, 5, 6. These are the fused bond, but original numbering of the quinoline is 1, 2, 3, 4, 5, 6, 7, 8. Right now, this is the 5 and 6 of the pyridine ring is involving in the fusion. Therefore, its name as benzo. Next, the position of the fused bond 5, 6. Then label with A and B. Therefore, the fused bond is the B 4, 6, 5, 6 B pyridine. This is the one of the name. And another name, azanophthalene is also the, sometimes we pronounce it as azanophthalene. Therefore, quinoline has three names. One is the quinoline, benzo 5, B pyridine, or we can also indicate this general benzo B pyridine, or one azanophthalene. This is the one case. These two are the isomers, structural isomers. One is the quinoline and another one the isoquinoline. The position of the nitrogen change. Here the position of the nitrogen is the first position. Here the nitrogen position is the second position. Now you can give the name 1, 2, 3, 4, 5, 6. The sixth bond, 5, 6 bond is the fused bond. This will be labeled as nitrogen carbon. First bond is the A, and this second bond is the B, and second bond, third bond is the C. Therefore, it's named as benzo 5, 6 C pyridine. 5, 6 C pyridine. Similarly, we have the indole. Common names are there. In most of the cases, we are using the common names, but some cases it requires to indicate the molecule with the IUPAC nomenclature system. Now, this is the indole. Its IUPAC name is benzo 5, 4, 5B pyrrole. This is the labeling 1, 2, 3, 4, 5. But original numbering is 5, 6, 7, 8. This numbering will be helpful to you. Give the position of the substitution present in it. But this position is help you to give the IUPAC nomenclature for the fused ring system. Benzo 4, 5. This is the A. This is the B. A, B pyrrole. Benzo 4, 5B pyrrole. Similarly, we have several compounds are there. Based on that, we can give the names. Okay. Right. In some cases, if the fused ring system containing all the rings are the heterocyclic rings. All the rings are the heterocyclic rings. Look at it. Here, this molecule, pyrimidine, pyrimidine type of molecule, pyrimidine molecule. Inside, this is the root word or base stem word, right? For this molecule, this is the base and prefix. That prefix name is the Pirru. Pirru. What is the name? This five-membered ring, less number containing less membered ring is indicated with the prefix, and large membered ring is indicated with the parent ring or base ring. Pirrolo 1, 5A pyrimidine. This, this ring is called as pyrimidine ring. Whatever the white circle, it is called pyrimidine ring. That ring system is called as pyrimidine ring. Right. Okay, someone is sending a message. Okay. Yeah. Right. This is the pyrimidine. This is the pyrrole. If one nitrogen is there at one first this position, only one nitrogen is there. Therefore, this is the pi-membered ring, azola pyrrole. Now, the pyrrole is the prefix. This is the base or root word, pyrrole. Then it's named as, first give the numbering 1, 2, 3, 4, 5, 5, comma. Then continue 6, 7, 8, 7, 8, and then 9. This is the position. Now, where it is fused? Where it is fused? 1, 5. 1, 5. This is the bond. A, B, C, A, B, C. Therefore, the bond A bond is involving the fusion. Therefore, pyrrole 1, 5 A pyrimidine. This is the root word. Now, we have several molecules are there. That molecule containing the different kinds of heteroatoms are existing as a fused. Different multiple number of heterocyclic rings are existing as a fused rings. In such case, we need to give the prefix. If it is a furan, we need to use the prefix as furo. If it is the imidazole, imidazo is the prefix word. Isoquinol, isoquinolo, or isoquino, you can also. If it is the pyridine, we can use the pyrido. Quinoline, quino. Thiophene, thiopheno, or thieno, thieno, we can also use. Thiopheno or thieno. Right? That is depends on the requirement. Okay. Here, one of the example is given. The multiple heteroatoms are there in the fusion ring system. Two ring systems are fused. One is the six-membered and one is the four-membered ring. What is the one is the pyrrole and another one is the pyron. Pyrrole and pyron are fused ring. How we need to give the name? Here, when the two heteroatoms are present in the two fused rings, the priority order, which one is having the highest priority, where we need to start the numbering. This priority order, the same priority, nitrogen, oxygen, sulfur, phosphorus, selenium, silver. This order we need to follow. In such case, based on this order, therefore the numbering starts from the nitrogen 1, 2, 3, 4, not the 4, 4, 5, 6, 7. This is the original molecule numbering. Again, I'm writing the molecule. This numbering is helpful when you are giving the name to indicate the position of the substituents. When any substitutions are there, in such case, we need to indicate the position of the substituents. Therefore, we need to give the original numbering. This is the actual original number 1, 2, 3, 4, 5, 6. But when you need to indicate the fusion, the bond which is fused, the original numbering, suppose this is I am considering. Right. 4, right. Just a minute. Right. The screen is visible? Right. Okay. In such case, we need to follow this order while you are giving the numbering. This is the molecule. Right. Now, for indicating the fusion bond, we need to indicate the numbering 1, 2, 3, 4, 5. This is one numbering. Suppose if it is for showing the or position of the substitutions, which if it is any substitution is there, suppose this position is having a clothing. For example, 1, 2, 3, 4, 5, 6, the seventh position. Seventh position. Now, how the compound name is given? For this compound, this name is the pyrano 2, 3, P pyrrole. Right? Why we are giving this? The highest priority in a heteroatom is present in the 5-member ring. Therefore, this becomes the parent ring. The 5-member ring becomes the parent ring. Right? This becomes the prefix. Okay, the first rule is avoided. Here, in this case, 5-chloro, 5-chloro, then number 2, 3, and position A and B. The square brackets 2, 3, and B. What is this? The 5-member ring is called. You can call it as azole or pyrrole. You call it as pyrrole, or you can also use it as a azole. Right. Similarly, I have given some examples here. Right. This is the 3-ring systems are fused. 3 rings are fused here. Look at here. In this, we will divide the molecule into 2 sets. One is this circular molecule is called as quinoline. It's the base. This circular molecule is included as a prefix. Pyrazino. This is the pyrazine. Pyrazino. Quinoline. Pyrazino. Quinoline. This pyrazine bond where it is fused 1, 2, 3, and A, B. 2, 3, B. Pyrazino 2, 3, B, quinoline. Okay. I have given several examples. Based on that example, I will share these notes to you. Okay, you can read it and understand. Okay, that is about the nomenclature of fusion ring systems. Now coming to the concept called as pi excess and pi deficient components, or pi excess and pi deficient heterocyclic compounds. Heterocyclic compounds or systems. What are the pi excessive and pi deficient heterocyclic compounds? Before understanding this concept, we are previously discussing the aromaticity. In that aromaticity, we are discussing about the benzene many times. Right. This is the 1 kcal structure. Both will be, but we can also indicate it with the double head arrow. These two are the resonance structures. These resonance structures can be generated with resonance hybrid. These two are called as kcal structure. Now look at here, in this benzene, every carbon is having one unhybridized carbon, p bond, p orbital, right? P orbital. Total 6 carbons are there. For 6 carbons, 6 unhybridized p orbitals are there. Each unhybridized p orbital is having one electron, therefore having 6 electrons. The 6 electrons are delocalized. The 6 electrons are delocalized. Therefore, the 6 electrons are equally shared by the six carbon in the base. 6 carbons in the base. Therefore, this is called normal electron density. This is called normal pi electron density or cloud density or pi electron cloud. Now, whenever we are taking a 6-member heterocyclic, in the benzene, I am replacing with one carbon is nitrogen, replacing the nitrogen with one carbon in the carbocyclic ring. Or in the case of a 5-member ring, in the 5-member ring, one of the carbon is replaced with X. X may be nitrogen, or NH group, or oxygen, or sulfur. Right. Both will follow the Huckel rule. Both will follow the Huckel rule. That means it is having 6 electrons. In all cases, this molecule is also having 6 electrons. Therefore, it follows the Huckel rule. All are aromatic. All are aromatic. Once they follows the aromatic, the bond between the carbon-carbon and carbon and heteroatom is the equal. Because all the 6 electrons are delocalized, equally distributed, equally shared with it compound. But in the case of this heteroatom is more electronegative than the carbon. Some electron density is more towards the nitrogen. When we compare to the electron density on the carbon in the benzene, the electron density in the carbon density on the carbon in the pyridine is less. Whatever these 5 carbons are there, 1, 2, 3, 4, 5 carbons are there. These on this carbon, the electron density is very less when you compare to the benzene. Why? Due to its even it is having a lone pair of electrons on the nitrogen that will not share by the ring, on the hybridized orbitals. Only it will be sharing the whatever the electrons present in the sp2 hybrid orbital. Okay, that will be mutually shared, but there is no increase in the electron density. And nitrogen is having some more electronegativity when compared to the nitrogen. Therefore, it draws some amount of electron density on the remaining 5 carbons. It is the reason for the decrease in the electron density on the carbons. Therefore, such kind of molecules are known as pi deficient heterocyclic compounds. Now coming to 5-member rings, these all the 5-member rings, X is replaced with NH or oxygen or sulfur. These heteroatoms are ready to donate this pair of electron to the ring system. Now, how many atoms are there in the ring? 5 atoms. How many electrons are there in this? 6 electrons. Therefore, 5 atoms are mutually shared 5 electrons. 6 electrons. Therefore, the electron density is more when we compare to the benzene, normal benzene. Such kind of molecules are known as pi excessive heterocyclic compounds. Okay, this is the important phenomena in the examinations. They may be asked as a short question. Define pi excessive and pi deficient heterocyclics and with a suitable example. Okay. Here, somewhat whatever the Huckel rule we are discussing, the same is applied here. We are already discussing about the aromaticity. There is no need to discuss separately. Okay. Now, some examples are given for refugee heterocyclics. Actually, these molecules are included in our syllabus: benzofuran, indole, carbazole, phenolene, isoquinoline, and some acridine. These 6 molecules are included in your syllabus. You need to prepare for every compound's 3 synthesis and 3 preparations and their physical properties and their aromatic properties in exam purpose. I will explain for one of the compound. you need to follow this, right? Just a minute. Yes. Coming to discuss about the synthesis and properties of some of the heterocyclic compounds. As early, I have given the list of the compounds which are included in our syllabus. First, I start with the indole. Indole. Its structure structure. It is a 5-member azole or pyrrole is fused with the benzene. Is the structure and IUPAC name IUPAC name 1H Yes, when we have the trivial name, we don't use the IUPAC now. Okay, but I need to give the IUPAC name also. This is IUPAC name. Whenever you are asking any computational software, the name will be given like this. But we can also assign the IUPAC name 1H benzo B pyrrole, or we can also write 1H benzo B azole. Okay, or we can also include the 1H indole also. This is also correct. Okay, next occurrence. Indole is widely distributed in the natural environment, can be produced by a variety of bacteria as an intracellular signal molecules. It regulates the various aspects of bacterial physiology, including spore formation, plasmid stability, drug resistance, biofilm formation, or um, virulences like that. Okay, the amino acids, we know that tryptophan is a very popular one. This is the tryptophan. This tryptophan is existing with the indole heterocyclic ring system. MEH. Tryptophan is an amino acid. Sources of that indole. Tryptophan is an amino acid. And indolestic acid is the plant material. Indolestic acid. And we agree very popular indigo. The color indigo, you know that. Indolestic acid. The double bond. Okay. Next, indigo. It is the dimer of the indole. Simple indole. A double bond is there in between the two indole rings. This is the indigo. It is also from plant source. Plant source. This is also from plant source. We can also synthesize. But it is used as a plant insecticide. Okay. For protecting the plants from insects, we can use it as a insecticide. Right. Now coming to the resonance structures. What kind of resonance structures it can show? Different possible canonical forms of indoles. Canonical forms of indole. First, you start with the indole, whatever seen earlier. This nitrogen is having one lone pair of electrons. Right. This lone pair of electron is donated to this nitrogen single bond. This 5 bond is moving to here, the third position. And you assign numbering 1, 2, 3, 4, 5, 6, 7. Now it generates a resonance structure. Here it forms a positive charge. Okay, this is the first step. This is the first form. You can see that this is the second resonance structure. Later, sorry, it is the negative charge, not positive charge. Negative charge. Then it will donate to here. It will donate it to here. then it leads to this position. Now immediately it moves to this position. Here it carries positive charge, the nitrogen. The nitrogen carries the positive because it is donating the lone pair of electron to the ring. Now a positive charge is already there. Here the carbon nitrogen double bond is cis nitrogen double bond is there. And here it carries the negative charge. It carries the negative charge. Here. Now, again, this negative charge is donated to here. This will be moving to here. This is the third one. Positive charge is here. Carbon, carbon, carbon nitrogen double bond, carbon, carbon double bond. Negative charge is here. A bond is here. And other like this. Next. Again, it will be reversed. It will be reversed. Then this is moving to here. This pi bond is moving to here. That is the rearranging of the double bond. Negative charge is here. And here it is carries positive charge. This is the fourth one. This is the fifth one. After that, again, this negative charge is donated to the whatever the negative charge is present here. That will move into here. This positive charge will be disappear, or sometimes when this negative charge is donated to this nitrogen, it will establish the carbon nitrogen pi bond. These 5 electrons are moving to this position. That means there is no change in the positive charge. This double bond is off here. Right. Again, this negative charge is donated to here. This will be moving to here, and this will be moving to here. Now it produces the original one. This is the fifth one, and this is the sixth. That means it generates the 6 possible canonical structures. 6 possible canonical structures. In all the canonical structure, look at here, whenever we are observing, the negative charge is in this molecule is the third position. In this molecule, it is the 6th position. In this molecule, it is having the 4th position. In this molecule, it is having 1, 2, 3, 4, 5. 5A position. In this molecule, it is having 2nd position. That means all these positions, it is having higher electron density. Higher electron density. Once it is showing the negative charge on those positions, it indicates that it is having higher electron density on that positions. Right? It will be influenced. It will be influenced during the reaction. During the reaction. And or it will be influenced the chemical reactivity of this ingot. Right. Now, based on this, majorly It is undergoing the electrophilic substitution reactions at second position and third position, second and third position. Nucleophilic substitution reactions are takes place on the benzene instead of 5-member ring, but experimentally some nucleophilic substitution reactions also takes place on the 5-member ring, right? But you coming to the synthesis of this preparation or synthesis of that indole molecule. How to this indole is synthesized? We have several important reactions are there. These important reactions are highly influenced in the organic or heterocyclic synthesis. The synthesis of fission, synthesis of indole. In that the first one is by Fischer-Indole synthesis. Those who are attending the practicals, have we discussed this synthesis? Is there any where we discussed it? I think it is not discussed in the first year. Okay, it is in second year, right? Okay. Now, this is the most widely used method for the synthesis of indoles. This is the most widely used procedure for the synthesis of indoles. It involves an acid. That acid should be a Lewis acid. That Lewis acid will be catalyzed the rearrangement reaction after formation of phenyl hydrazone from the an aldehyde or a ketone which is reacting with the hydrazine. Okay, and after formation of the hydrazone, phenyl hydrazone, that is the phenyl hydrazine is reacting with a carbonyl compound. That carbonyl compound further undergoes the elimination of the ammonia that leads to the formation of indole. How this reaction is expressed? Starts with the phenyl hydrazine. Phenyl hydrazine, which is reacting with a carbonyl compound like I'm going to take here is acetophenol. Acetophenol, right? In presence of Lewis acids, the Lewis acid is catalyzing this reaction. First, it is producing the phenyl hydrazone derivative. Whenever you are doing your functional group analysis in the organic chemistry practicals, we frequently use the phenyl hydrazine for preparing the derivatives for the carbonyl compounds, right? For preparing the derivatives for the carbonyl compound, we are very frequently using this reaction, such kind of reaction. Okay, this is called phenyl hydrazone derivative. Phenyl hydrazone. What phenyl hydrazone it is? Acetophenone, phenyl hydrazine. Phenyl hydrazone. Now, this step of reaction is the formation of this acetophenone and phenyl hydrazone is the nucleophilic addition reactions. Nucleophilic addition reaction. It means it follows the nucleophilic addition reaction mechanism. Right. Later, it undergoes the cyclization by the elimination of ammonia. Cyclization by the elimination of ammonia that leads to the formation of 2-phenyl indole is the product. Two-phenyl indole is the product. Now, this kind of reaction is called Fischer-indole synthesis. In this Fischer-indole synthesis, now this second step for cyclization, we are going to use the Lewis acid. Lewis acid may be a polyphosphoric acid, zinc chloride, anhydrous zinc chloride, or a BF3, or RALS, any relevant Lewis acids. Okay, here it is undergoing the elimination of water molecules or ammonium molecule that leads to formation of 2-phenyl indole. Right. This reaction is known as Fischer-indole synthesis. Fischer-indole synthesis. Right. Then what is the mechanism involved in this? The mechanism is very important for exam purpose. Mechanism. Just a minute. Okay, I want to write the mechanism. Now the reactions we are starting with this phenyl hydrazine and acetophenone. Now I am going to write the mechanism. First write the phenyl hydrazine. This will the starting material is initiating the reaction. Now it is reacting with a carbonyl compound. The alpha methyl group is important for cyclization. Whatever it may be, you can take phenyl or any R group, you can substitute it. Right. Now the reaction starts with the nucleophilic addition on the carbonyl carbon. Then the polarization of the pi bond in presence of an acid. Is there any Lewis acid? It will be initiated. Then first undergoes the addition O minus CH3, or it carries the positive charge. To neutralize this positive charge, this carbon hydrogen bond pair will be taken by the nitrogen. This proton is abstracted by this negative charge. So OH and R. Again, the lone pair is again donated to the Again, it donated to this bond, and simultaneously elimination of this OH group. Whatever the nitrogen is there, that is also eliminated. Then that H plus and OH means both will be combined together, that elimination of water. Then it gives the first step product. The methyl will be here and R will be C. Right. The next one. Here it undergoes the keto imine. A tautomeric form will be generated. This is the imine form of the nitrogen. Then that will be right. Next, a pair of electrons are donated to the ring. Simultaneously, this 5 electron density is donated to this, and this will be donated to here. And simultaneously, the nitrogen bond will break down. That leads to the formation of an intermediate. The CH2. That CH2 you can indicate like this. Hydrogen, hydrogen. This is the NH, and another NH is here, and R. Okay. Next, here the hydrogen is there. Then it is undergoing shifting. How it is undergoing shifting? This carbon hydrogen bond will be broken, and it will be whatever the benzene ring is there, that will be undergoing re-aromatization. Now this pi bond is donated to this center. This carbon nitrogen bond, pi bond will be moved to nitrogen. Then what is the intermediate generated here now? Hydrogen is one, the second hydrogen is there. The R group is there, along with whatever the proton is here leave, that will be taken by this nitrogen that is existing as the NH2. Right? Then there is the shift one. This is the sigma bond involving the shifting 1, 2, 3, 4, 5. Right? It is simple shifting reaction. Now elimination of ammonia. Just you heat it, then it eliminates the ammonium gas. Gas it is. Then it's the formation of it is the R is the phenyl group. There is the 2-phenyl involved. 2-phenyl involved. Right. Is the mechanism involved in the synthesis of indole using the Fischer indole synthesis. We have several this kind of synthesis are there, such as the second one, Medlung synthesis. In this matrix synthesis, it involves the cyclic dehydration of an acyl orthotoluene in presence of strong base and at higher temperature. Indole itself can be prepared by this method. 2-alkylidone can be synthesized by the cyclo-dehydration of ortho-acyl aminotoluene by treatment with a strong base such as potassium tertiary butoxide or sodamide. The reaction is shown below. This is the starting material. This is the orthotoluene. Whenever it is treating with acetic anhydride. This is the acetic anhydride. Simple, just mix in presence of a catalytic amount of acid or like acetic acid. Then it leads to formation of N-acyl orthotoluene. N-acyl orthotoluene. This N-acyl orthotoluene is treated in presence of a base, like so sodium hydroxide, strong base, and heated. Then it leads to the formation of two-methyl indole. 2-methyl indole is the product. This is called Madelung synthesis. It's a very simple reaction. It is a benzylic position. This benzylic position easily undergoes the nucleophilic substitution reaction on the carbonyl compound. Then it initiates the reaction. Right. Next, third synthesis. You can also have the other reaction in the Madelung synthesis is N-ortho-formaldehyde. You take the same orthotoluene, you treat it with the formal chloride. You treat it with the formal chloride. Then it leads to the formation of ortho-tolyl formamide. N-ortho-tolyl formamide, which is treated with a potassium salt of tertiary butoxide. Just boil it at a high temperature. Then it leads the formation of a pure indole. Without substitutions, we can get the compound from this tolyl formamide. Just we are taking this to N-tolyl formamide. N-tolyl formamide can be synthesized from the orthotoluene, which is formylation, the formal chloride. Then it leads to formation of another tolyl formamide. Then it leads to formation. Then it is in treated to the tertiary butoxide, potassium salt of tertiary butoxide, which is on heating, it leads to the formation of indole molecule. Next, Bichler-Sneplovsky reaction. Third one is Bichler-Sneplovsky reaction. Bichler's synthesis. Here also we are starting with the aniline. The reaction starts with aniline and treated with 2-bromo. 2-bromo. This one. 2-propanone. 2-bromo. 2-propanone. Substituted 4 carbons. 1, 2, 3, 4. 2-bromo. 2-butane. Then it is in presence of 2 normal HCl and reflux it. First, it is undergoing the formation of the bromine is substituted. NH2 actually. Then NH. This kind of intermediate will be generated. Later, it is undergoing cyclination. It is undergoing cyclination. That leads to the formation of 2,3-dimethyl indole will be generated. 2,3-dimethyl will be generated. Here also we can see the mechanism. What is the time now? 1 second. Okay, we have time. Right. Mechanism of this reaction. But wherever we are discussing the mechanism, that is important to learn. The same will be asked in the examination, right? This is the aniline. The nitrogen is having lone pair of electrons. This will be donated to this here because it is the highly polar bond. It is ready to leave as a bromide ion. As HBr. This reaction is carried out in the 2NHCl, therefore it is eliminated as HBr. Right. This is the intermediate generated. After the formation of intermediate, it will leave the proton by the nitrogen-nitrogen bond will be cleaved. Therefore, minus H plus will be eliminated. Minus H plus is eliminated. Later, the same pair again donated to the ring. This pair will be donated to this carbonyl. 5 electrons are donated to this carbonyl. Then that lead to the formation of this positive charge. This is the O minus because once you donated this 5 electrons to this carbonyl carbon, the 5 electron moving to oxygen. Therefore, it carries a negative charge. Here the CH3 group is there. Here another CH3 group is there. So this positive charge will be neutralized by the. Now nitrogen carries the positive charge. Later, here the hydrogen is there. This carbon-hydrogen bond will be broken. That will be re-aromatization. During the re-aromatization, This will be carried by this negative charge. At the same time, these pi electrons are moving to nitrogens. Right? So the OH, CH3, CH3. Now here elimination of water molecule. Elimination of water molecule. Then elimination of water. That leads the final product. Two, 3-dimethyl ether. Right, like this, you need to prepare 3 different syntheses for every heterocyclic compound present in our syllabus. We have the phenolines, isoquinoline, acridine, carbazole, and benzofuran. These 6 molecules are there in our syllabus. You need to prepare your own notes by using your material or any other sources. Okay. For every compound, you need to prepare 3 reactions, that is the synthesis reactions, and 3 chemical properties. 3 chemical properties. That is enough for the heterocyclic compounds preparation for exams. Okay. We have other synthesis also there. That is also important, but what is important, what is not important, you need to decide based on the previous papers. Okay. Whatever the questions appear in the previous examination paper from the heterocyclic syllabus, where those topics you need to mark it and prepare for the examination. Okay. I think that today's session is time is over. Otherwise, I will continue for 5 to 10 minutes. Okay. See the physical properties. I will give you another reaction for the preparation. Fourth reaction. The fourth one is research indole synthesis. Research indole synthesis. This research indole synthesis, we are going to take 2-nitrotoluene. 2-nitrotoluene. That is treated with diethyl oxalate. Diethyl oxalate. Diethyl oxalate. And boil it or warm it at 40 degrees centigrade. Then add sodium methoxide, C2H5ONA, sodium methoxide. And in the second step, just boiling water, that is a dilute acid water, aqueous acid. And in the third step, we just treat it with zinc acetic acid. Then it leads to the formation of indole will be generated. Okay. These are the 4 kinds of synthesis are there. Now coming to the physical properties of indole. Physical properties of indole. Indole is a colorless crystalline solid. Indole is a colorless crystalline solid. Its melting point approximately 52 degrees centigrade. And suppose if whenever you are heating, it is melted down and it's boiled at 254 degrees centigrade. 254 degrees centigrade. It is soluble in most of organic solids. Soluble most of organic solvents, but slightly partially also soluble in water, but it takes a lot more time. The pure form of indole has very pleasant smell. This is the and this is the reason is it is used in the perfumery base. The impure indole has very unpleasant smell. The main commercial source of indole comes from the 220 to 260 degrees centigrade fraction of the coal tar distillation. It is distilled from the from coal tar. Coal tar. This will be isolated at 220 degrees centigrade to 260 degrees centigrade fraction. Right. Next. Chemical properties. What are the chemical properties it can show? As let's see, indole is a 5-axis aromatic heterocyclic compound because it is a 5-membered nitrogen heterocyclic is fused with benzene. Therefore, it is an example for the 5-axis aromatic cyclic heterocyclic with 10 5 electrons. Then indole is an aromatic compound. It follows the Huckel rule, that is a 4n plus 2 electron rule, and therefore it is aromatic. Right? Indole is the, look at here, whenever we see the structure, here the 2 electron lone pair of electrons plus 2, 4 plus 6, total 10 electrons are there. Therefore, it follows the 4n plus 2 5 electron rule, Huckel rule. Huckel rule is followed. Therefore, it is aromatic. Is aromatic. And the lone pair of sp2 hybrid nitrogen atom is also nitrogen atom is also participating in the delocalization. You can hear is the lone pair is also participating in the delocalization. That is the reason it is aromatic, right? Due to the 5-axis nature of aromatic system, the reactivity and chemical properties of indoles always influenced by this 5-axis nature. Indole is a weak base due to the presence of NH, secondary amino nature. It is a weak base. It is having the pKa value is up to minus 2.4. In presence of strong acid, protonation of the nitrogen atom may take place. That means whenever you are treating with HCl, a concentrated HCl, it gives the indole salt. It is treated with concentrated HCl. That leads to the formation of protonation of the nitrogen. This chloride will be, sorry, positive charge will be stabilized within chloride. That is the indole hydrogen chloride salt. Salt is element. Therefore, it is the slightly weak, weak basic in nature. Due to that reason, it is reacting with the acid, strong acid, then it is undergoing the protonation that leads to the formation of salt. Like other aromatic compounds, the indole is also participating in the electrophilic substitution reaction. It is also participating because it is the aromatic in nature, therefore it is electrophilic. It is undergoing electrophilic substitution reaction. Where this generally takes place because of electron rich or 5-axis nature of this 5-membered ring, the electrophilic substitution reactions that takes place at second and third position. At the electrophilic substitution reactions at second and third position. Okay, there is an equal chances are there. It is clearly explained by the that canonical structure, resonance structures are already discussed in the earlier. Based on that, it is involving in electrophilic substitution reactions at the second and third positions. Okay. Then, especially the nucleophilic attack, the nucleophilic attack is favorable at the second position. Nucleophilic attack is favorable at the second position. Now we have the several reactions are there for the chemical reactivity. But you, for example, you take the simple indole, which is subject to the several reactions. Suppose if it is under bromination in the presence of dioxane solvent at 0 degrees centigrade, it leads to the formation of 3 bromo products. 3 bromo indole will be generated. The same at this indole is reacting with the nitroethane C2H5ONO2 at 0 degrees centigrade. So ethyl nitrate is ethyl nitrate is reacting with ethyl nitrate. Then it leads to the formation of the nitration at third position. It leads to the formation of 3 nitro indole will be generated. Next is sulfonation. This is nitration reaction. This is bromination reaction. Nitration. And next is sulfonation. The sulfonation is carried out in presence of sulfur trioxide gas, in presence of pyridine, and when you boiling it, then it leads to formation of sulfonation at third position. Indole sulfonic acid is generated. This is called sulfonation reaction. All these are electrophilic substitution reactions. Electrophilic substitution reactions. Okay, Friedel-Crafts alkylation. It can also be found involving the Friedel-Crafts alkylation. It is treated with methyl iodide in presence of DMSO, DMF and DMSO, and boiling. Just it leads the formation of alkylation takes place at the third position. Alkylation takes place at the third position. Next, it is also reacting with diazonium chloride, aryl diazonium chloride. In presence, it leaves the HCl, then diazotization takes place. Diazotization is taking place. Yeah, the nitrogen is there. Nitrogen, and whatever the aryl group is there. This is diazotization. Diazotization reaction. This is called Friedel-Crafts alkylation. Right. Whenever it is subject to the Riemann-Tamer reaction, you know that Riemann-Tamer reaction. What is the Riemann-Tamer reaction? It is treated with the chloroform in sodium hydroxide that leads to the formation of an aldehyde. Is indole 3-carboxaldehyde. Indole 3-carboxaldehyde. Carboxaldehyde. This is called Riemann-Tamer reaction. Riemann-Tamer reactions. Okay. These are all the several different kinds of reactions it is involved. Okay. Like this, you need to prepare your own notes for the remaining 5 compounds. What are that? Benzopyrrone, quinoline, isoquinoline, right, carbazole, and acridine. For these compounds, you need to prepare your own notes, and it will be helpful for the preparation of your examination. Okay. Up to this, heterocyclic chemistry is ended. Then next, I'm going to start the next class is natural products, last block. Okay. Now I'm going to conclude the session. Thank you. If you have any doubts, you can ask me. Okay. No more doubts. Can I leave? Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.